Welcome to the next lecture. Today we will study something called amplitude modulation with carrier. So before I start it, I would like to recall you that till now we have done double sideband suppressed carrier, right? So what we will do is a simple design. So here is the modulator. You have a message signal m of t. You multiply it with the corresponding carrier signal, high frequency carrier signal. We call that, suppose, cos omega ct, and now how to demodulate it. Demodulation in case of DSBSC is same almost same to modulation, in the sense that here is your modulated DSBSC signal, you multiply it again with carrier signal, and then you put a low pass filter, and you will get some constant times of t, sorry. So you know what happens actually. So the output of this filter is m of t cos square omega ct, which can be written as m of t by 2 plus m of t by 2 cos 2 omega ct. So this signal is a low pass signal and this is high frequency signal. When you pass it through low pass filter, you will get here half m of t. Half is just a constant, doesn't matter. So sorry. So the moral of the story is, for DSBSC demodulation, just a moment. Yeah, so for DSBSC demodulation, you need to generate this carrier locally at demodulator also, which is very difficult in practice to generate exact cosine signal. Suppose you generate cos omega ct, there is always some phase associated with a signal. Now if you generate this at transmitter, it is very difficult at receiver to generate, suppose, same cos omega ct plus there will be some phase lag theta 2. It is not possible practically. And if at all you want to generate exact carrier frequency, the circuit is very complicated. It needs something called phase locked loop, synchronizer. There are a lot of circuits needed. Now what is the solution for this? So here is one solution. So this is m of t cos omega ct. Okay, so this is your modulated signal. What you do is you add carrier signal to it, a cos omega ct. Okay, so this part is your DSBSC. You called it double sideband suppressed carrier. There is no carrier, but this is carrier part. Okay, and this is actually called AM signal, amplitude modulation. We will see the miracle of adding this carrier later on. So we can write it as a plus m of t cos omega ct. Now this a is the amplitude of maximum amplitude of cosine signal. Its value will matter a lot, we will see it. But right now, what is the Fourier transform of this? Okay, so it has two parts. If you see the Fourier transform, this part m of t cos omega ct, it has the usual Fourier transform, 1/2 of m of omega plus omega c plus m of omega minus omega c. And you know the Fourier transform of cosine is simply pi times delta of omega plus omega c plus delta of omega minus omega c. Sorry. Now Just a moment. Yeah. So if you have message signal whose Fourier transform is something like this, then the Fourier transform of AM with carrier will be, and there is one pi a impulse. This is at omega c, this is omega plus omega c, this is omega minus omega c, this is minus omega c, this is minus omega plus omega c, this is minus omega c. So what is extra here is there is an impulse. So what is the bandwidth? As all of you know, bandwidth will be this much, that is 2 omega, sorry, see, you had to first see, suppose this is 2 pi b minus 2 pi b. Okay, so if this is omega c, so what is this point? This will be omega c plus 2 pi b. Yeah, so I'm sorry for this typo, and this will be omega c minus 2 pi b. Okay, at this point will be minus omega c plus 2 pi b, and this point will be minus omega c minus 2 pi b. So bandwidth will be this width. Okay, so which is 4 pi b. So this 4 pi b is the bandwidth in angular. I will write omega b. Okay, so but actual bandwidth will be omega b divided by 2 pi, which is 2b. So bandwidth of AM is 2 times b. Similarly, bandwidth of DSPSC is also 2 times b. If b is the bandwidth of message signal, the bandwidth of modulator signal is 2 times b. Now coming back to the AM with carrier, that is A plus m of t cos omega ct. We know that cos is having values, cos takes values between -1 and 1. So this phi am of t can take minimum value of minus a plus m of t up to a plus m of t. Okay, simple property of cosine signals. And how to plot it? Now, as an example, suppose your message signal looks like something like this, with a maximum value of mp and a minimum value of minus mp. Okay, now let's see two cases. So one is that a plus m of t is always positive. So message, the value of amplitude is such that a plus m of t is always positive. Sorry. Now in that case, how to plot? See, you have a cosine. Okay, so you know how to plot cosine. Simple. High frequency cosine signal. But now you have a plus m of t times cos omega ct. Okay, and I'm assuming that a plus m of t is always positive. So what will you do is, we will put this message signal, let me use different color. This message signal, we will put it like this. What is this? This is basically a plus m of t, right? This is minus of a plus m of t. because cosine will vary in between these two values only, and in between is the cosine. Okay, this is how it will look like, and we call this as envelope. Okay, it looks like as if you are putting an envelope over the cosine signal. The shape of envelope is proportional to the message signal. That is important. But if value of a is such that a plus m of t is less than 0 sometimes, so it means that the, just a moment, I will plot it. This is your x-axis, y-axis, and see, this is the message signal I am plotting here. This is m of t plus a, but value of a and m of t is such that it can be negative also. Okay, similarly, like this. Now, if you now put cosine signal in between, it will look like this. We will later see that we can recover message signal from this AM signal, but we cannot recover message from this AM signal. Okay, this will be clear when we will do the envelope detection, something called envelope detection. Now, we know that peak value of message signal is m of p. We write like this. Go back to this. This is m of p minus m of p. Okay, the value of message signal varies between m of minus m of p and m of p. Okay, so we need a condition. Now, what amplitude we should choose for a carrier signal? Here is this: a plus m of t should be greater than or equal to 0. Because if you chose a such that it is less than 0, you will see it later that you cannot demodulate the signal. But if a plus m of t is greater than 0, you can demodulate the signal. Now, this condition is equivalent to, see, m of t is always greater than or equal to minus mp, right? Mp is the minimum value. So this condition is equivalent to a minus mp greater than or equal to 0, hence a should be greater than or equal to m. So this is the condition to choose the amplitude of carrier signal. It should be always at least or greater than the amplitude of maximum amplitude of message signal. Okay, so for that we define something called modulation index. Mu, which is defined as amplitude of message divided by the maximum amplitude of carrier, mp by a. Okay. Now, since for proper demodulation we require that a should be greater than or equal to mp, which implies mp over a should be less than or equal to 1. Okay, and since it is always positive, so 0 is less than or equal to mu less than or equal to 1. Now, in terms of mu, we can write this AM equation as, see, it is a plus m of t times cos omega ct. So we can write it as a, we can write as it is, mp we can write as a mu, hence that can be written as a into 1 plus mu times cos omega ct. Okay, now we will give an example that will make it more clear of something called tone modulation. What is tone modulation? Tone modulation means that It's a case where a message signal is also cosine signal. Suppose m of t is equal to b cos omega mt. Okay, and your carrier signal c of t is a. I will take that also cos omega c, and this omega c is much greater than omega m, right? Omega m is just like, you know, audio signal, one pitch of audio signal. Now how will phi am of t look like? It will be a cos omega ct plus b cos omega ct cos omega mt. And what is mu? Mu is the maximum amplitude of message signal, that is b, divided by maximum amplitude of carrier part, that is a. Mu is equal to b by a. So we can write phi am of t as a into 1 plus, so let me write it as a cos of omega ct plus mu a. Okay, sorry, I think here we have m of t also. Yeah, a cos omega ct cos omega mt, which is a into 1 plus mu a into 1 plus mu cos omega mt times cos omega ct. Okay, now suppose you choose a and b such that mu is 0.5. Okay, so what will be phi am of t? It will be a into 1 plus 0.5 cos omega mt cos omega ct. How to plot it? See, first you should plot this part. This is called envelope part. It is slowly varying signal. Okay, so let's say like this. You check one thing. See, here it is 0.5 cos omega mt. So the maximum value it can take is 0.5, and minimum value it can take is minus 0.5. So 1 minus 0.5 is 0.5. So it will be always, the minimum value will be always 0.5 from the x-axis. Okay, and then in between you plot the cosine part, high frequency part. Okay, now let's take another case. If mu is equal to 1, then what will happen is, you will get phi am as 1 plus then directly cos omega mt times cos omega ct. So what is the maximum value of cos? 1. And what is the minimum value of cos? Minus 1. So at that point this will be 0. So the envelope will touch now x-axis, something like this. Okay, and this will be the AM signal. Okay, so one of the important factors we have to take care of is how much is the carrier power and how much is the power in sidebands. What does that mean? Suppose if you see this phi am of t, it is equal to a cos of omega ct plus m of t cos of omega ct. So this part is carrier part and this part is sidebands, right? Now what is the, how much is the average carrier part? The average power corresponding to carrier part PC is, you know, the average power of a cos omega ct, right? You have to do it like this: 0 to t over a time period t, a square cos square omega ct dt. This is the total energy and divided by time. So just do at your places, you will get it a square by 2. So it is a square by 2. Okay, and m of t is a message signal. Suppose you denote the average power of message signal as, this is the average value of message signal m hat. So the average power of sidebands will be same 1/2 of m hat square of t. Okay, see, m hat is the average value of message signal. Okay, now we define something called efficiency of this am. See, why we need to define efficiency? Because in case of DSB-SC, you are having only m of t cos omega ct, and this part exactly contains message signal, so no power was misused. But in AM, we are transmitting this extra part, which is not useful because it does not contain message part, but it helps in demodulation. We will see that. So we need to define efficiency. Eta as useful power divided by total power. So what is useful power? Useful power is a sideband power, PS, and total power is carrier power plus sideband power, which can be written as the mean square average of message divided by a square plus mean square part of average in percentage. Okay, so again, as a simple example, if we consider tone modulation, if you consider the tone modulation, you have m of t is equal to mu a cos omega mt, hence mean square value will be mu a square by 2. Okay, you just have to square it and integrate it. So efficiency will be mu square divided by 2 plus mu square. This will be the efficiency in case of AM with tone modulation, and clearly we know that 0 less than equal to mu less than equal to 1, and you have to find, suppose if I want to find what is the maximum efficiency we can get, for that you will need to differentiate with this with respect to mu and put that equal to 0. Okay, and you will note that for derivative to be 0, you need mu equal to 1. At mu equal to 1, you will get maximum efficiency, that is eta max, and that will equal to 1 over 3, which can be written as 33%. It means that out of suppose 100 watts, 33 watts are used for transmitting the message. The rest of the part is used, just wasted. But why we still go for AM is because it helps in demodulation. We will see that. Now, before we go into the demodulation, we had first see how to generate AM signals. Generation of AM signals. How to generate it. So to see the generation, we will have very simple AM generator, very simple, cost effective. So there will be a message signal here. We will feed it here, and a carrier part, suppose C cos of omega ct here. Okay, so this will be plus minus, this will be plus minus. Here I put a switching device, a simple diode between A and B. Okay, this I call as E dash, and this I call as B dash, and there is a parallel shunt resistor here. Okay, and then we put band pass filter centered around omega c, and this is your C and C dash. I call this output as V naught of t. Now let's see how this will give us AM signal. First of all, what will be the input to the diode? So that is M of t plus C cos omega ct. Now we know that message signal is a low frequency signal. Cos part has a very high frequency, right? So the overall sign or the overall change of sign will be determined by cosine part, not by the M of t part. Definitely we will keep this C high. So the on and off, turning on and off of diode will depend upon how fast the cosine signal changes its sign. And what happens is, in the positive part of this cosine signal, diode will be forward biased, it will be short circuit on, and in negative half, diode will be reverse biased, it will be off. So in other words, the effect of diode is such that this M of t plus C cos omega ct, it gets multiplied with on off signal, which we call as W of t. Okay, it is the on off signal of this type. On off, return to 0. Okay, on off, this is W of t. So this is your V out, V BB dash of t. This will be the voltage across VBB dash, which is here. This is VBB dash. Okay, now you know that since this on off is happening periodically and it happens at the same frequency as that of carrier signal, so this on off can be represented by Fourier series. The Fourier series of this on off signal is, we have already done it, 1/2 plus 2 by pi cos omega ct plus sorry, the second is minus 1 over 3 cos 3 omega ct plus 1 over 5 cos 5 omega ct, so on and so forth. You know this. Now we will multiply it term by term. Okay, so one term will be M of t by 2. Okay, and similarly 2 by pi M of t cos omega ct, so on and so forth. These are terms multiplied by M of t. The other part will be C cos omega ct by 2, right, plus 2 by pi C cos square omega ct minus C by 3 into 2 by pi cos 3 omega ct, so on and so forth. Now we are using a band pass filter. See, band pass filter has and centered around omega c. Okay, so it will be something like this. It will allow only frequencies closer to omega c. So to omega c, or even the message signal which is at center around 0, or any other signal at 3 omega c, they will not be allowed by the band pass filter. So I will mark the parts with red color. Filter will not allow m of t. This filter will allow because it is at frequency omega c. This will be also allowed, it has a frequency omega c. This is square part. When you will break it, it will contain two parts. One is 1 plus cos 2 omega ct. So one part is 2 omega ct, it will not be allowed. The constant part also will not be allowed because that is around centered around 0. So all other terms you will see that contains higher harmonics of omega c, they will not be allowed. So after passing through band pass filter, this VBB dash of t, you will get c over 2 cos omega ct plus 2 by pi m of t cos omega ct. So you can call this as a cos omega ct plus, and this you can call as mu a cos omega ct. So we can write as a plus mu, sorry, this is, there should be m of t also, yeah, mu m of t times cos omega ct. So other terms will be suppressed by band pass filter. So very simple design. Okay, so this is the modulator for AM signals. Now what will be the demodulator for this AM signals? Today's lecture will be a little bit longer, but I would like to complete it. I will show you a very simple detector, something called envelope detector. So we'll do now demodulation of AM signals. This is the power of AM. That is the main purpose of adding the extra carrier part. Here is a very simple demodulator. So this is your phi AM of t. This is the AM signal. Okay, there is a simple diode over here. There is a simple capacitor here, a shunt load resistor, and this is your VC of t. Okay, now let's see what will happen. Let's plot this tone modulation based AM. So the envelope is something like this. Okay, and this is the AM signal. Okay, this is the x-axis. Now when we will pass this through the diode, you see what will happen. I will now mark with, let's say, green color. Okay, so when, suppose this is the start of the signal, before this diode is reverse biased. Okay, so it will not allow this part. Now this part onwards diode is forward biased. Okay, and when diode will allow this signal, meanwhile the capacitor C gets charged. Okay, so it gets charged this till this point. After that there is a drop in potential, but capacitor will now start discharging. Okay, when capacitor will start discharging, it will discharge like this decaying way. Okay, now at this point signal value again is now has risen. So see, In between, diode will be in reverse bias again, but during that time capacitor will discharge. Okay, then again capacitor will charge, it will elevate. Okay, now again after this point capacitor will discharge, but slowly like this. So then reverse bias, again discharge, again discharge, again discharge, again discharge, again discharge. Now if you separately plot the output of capacitor, you will get this. Okay, so this is approximately equal to the message signal, which is like this. Okay, this is the basic logic for something called envelope detector. See now the power of AM. We don't have to generate uh, cosine signal separately. Why? Because cosine signal we have transmitted along with the modulated signal, DSBC signal. That is the power of you know AM. So now you would have seen that although there is a disadvantage in terms of energy efficiency, see here 33% power efficiency is there. Power is getting wasted because we are adding carrier part, right? But why we are doing this? See the power. The demodulation part is very simple. No filter needed. Just with three elements, diode, capacitor and resistor, you can design a radio receiver for AM. So that is why it was preferred for radio broadcasting. So this much is for AM. Next lecture, we will continue with something called single sideband modulation. Thanks.